80 microseconds. That is the approximate difference between the tick of a cesium atomic clock on Earth and the same clock aboard a GPS satellite after relativistic correction is applied. Time travel is not what you think it is, and tonight, we are going to walk through what it actually feels like and what it actually costs. You do not step into a glowing tunnel, you step into a laboratory that smells faintly of coolant and ozone. The floor hums beneath your boots because beneath it sits vibration in isolation for an optical table. And the room is colder than comfortable because temperature drift ruins precision. A lesser-known technical fact: modern cesium atomic clocks keep time by measuring microwave radiation at exactly 9,192,631,770 cycles per second, a number chosen to define 1 second in the International System of Units. You were told not to lean on the table, not to exhale too close to the apparatus. Even breath carries moisture and heat in both bend measurement. A lesser-known production and logistics reality: high-precision timing laboratories often consume tens of thousands of dollars per year in environmental control alone, including redundant HVAC systems to maintain temperature within fractions of a degree Celsius. What you feel first is not motion. It is anticipation. The screen shows 2 time readouts drifting apart by nanoseconds, and you realize that one of them is technically in the future relative to the other. A lesser-known battlefield adaptation of physics occurred in 1971 when the Half-Keating experiment flew atomic clocks on commercial airliners to measure relativistic time dilation, adapting passenger aircraft into moving laboratories. Here is the mechanism. According to special relativity, motion affects time. The faster you move relative to another observer, the slower your clock ticks compared to theirs. A lesser-known doctrine and training detail of satellite engineering is that GPS technicians are trained from the beginning to think in relativistic terms because satellite clocks gain about 45 microseconds per day from gravitational time dilation and lose about 7 microseconds per day due to velocity effects. You stand there watching numbers separate. It is silent except for the air system. There is no flash, no distortion of space, no cinematic ripple. A lesser-known medical and psychological fact: human perception cannot register time differences below roughly 10 to 20 milliseconds, which means relativistic effects are entirely outside direct sensory experience. Now the explanation widens. The satellites orbit at roughly 20,200 kilometers above Earth and travel at about 3.9 kilometers per second. Those speeds and altitudes are enough to create measurable time drift. A lesser-known countermeasure built into GPS design is the pre-adjustment of onboard atomic clocks so that they tick slightly slower on the ground before launch, offsetting predicted relativistic gain in orbit. You imagine stepping into a spacecraft instead. You imagine engines roaring and stars streaking. But in reality, astronauts aboard the International Space Station experience time dilation of only about 0.01 seconds over 6 months. A lesser-known procurement politics fact: funding for precision timekeeping research has often been justified through military navigation needs rather than pure science, shaping which experiments receive long-term support. Inside the ISS, the air smells recycled and metallic. Velcro strips hold everything in place. You float past a viewport and see Earth slide beneath you in 90 minutes per orbit. A lesser-known technical specification: the ISS orbits at approximately 400 kilometers altitude and travels at about 7.66 kilometers per second, fast enough to circle the planet 16 times per day. Your body does not feel time slowing. What it feels is fluid shift. Blood moves toward the head in microgravity, sinuses feel full, and legs thin out. A lesser-known production and logistics constraint of long-duration spaceflight is the need to ship roughly 3 to 4 kilograms of food and supplies per astronaut per day, making every launch mass calculation critical. The explanation behind your slight time travel is simple but unforgiving. Time dilation at orbital speed is measurable but small because velocity remains far below light speed. The equation of special relativity shows that effects become dramatic only as velocity approaches 299,792 kilometers per second. A lesser-known battlefield adaptation of theoretical physics occurred when particle accelerators, like CERN's Large Hadron Collider, used relativistic corrections to predict lifetimes of unstable particles moving near light speed. You imagine pushing faster, much faster, near light speed, but that requires energy beyond conventional chemical rockets. A lesser-known doctrine and training fact of astronaut corps preparation is that trainees study not only mechanics of spacecraft, but also limits of propulsion systems, because acceleration forces above about 3 to 4 g for extended periods can cause loss of consciousness. Acceleration presses you into a seat. Your chest feels heavy. Vision narrows if g-forces rise. A lesser-known medical detail: sustained exposure. Above 5G without protective measures can cause blood to drain from the brain, leading to Galop G-force induced loss of consciousness. Now the mechanism again. To reach even 10% of light speed, kinetic energy required is enormous. For a 1-ton spacecraft, energy demand would be on the order of 4.5 times YOY joules, comparable to the output of many nuclear power plants running for days. A lesser-known countermeasure concept explored in propulsion research is ion propulsion, which provides low thrust but high efficiency over long durations, though nowhere near relativistic speeds. In the lab again, the numbers continue to drift. You realize that time travel is incremental, statistical, bureaucratic. It is paperwork and calibration reports. A lesser-known procurement, politics, reality. Development of atomic clock technology accelerated during the Cold War because accurate missile guidance required precise synchronization of time signals. The emotional reality is anticlimactic. You traveled forward in time by microseconds, maybe milliseconds, over months. No paradoxes, no meeting of ancestors. A lesser-known technical specification the best optical lattice clocks today can achieve: stability at the level of 1018, meaning they would lose or gain less than 1 second over the age of the universe. Here is what that means. Time travel is happening constantly. Every airplane flight moves passengers a few nanoseconds into the future relative to people on the ground. A lesser-known production and logistics note: commercial aviation relies on GPS timing corrections. Without relativistic adjustments, navigation, errors would accumulate at roughly 10 kilometers per day. You'd feel turbulence in an aircraft at 10 kilometers altitude. Engines hum at steady thrust. The seat vibrates slightly. A lesser-known battlefield adaptation of navigation occurred during the Gulf War when GPS receivers were rushed into wider deployment. Adapting civilian satellite infrastructure for military maneuver in desert terrain. Explanation again: gravity affects time. The deeper in a gravitational well you are, the slower time moves relative to a higher altitude observer. This is gravitational time dilation, predicted by general relativity. A lesser-known doctrine detail of satellite maintenance is routine clock correction uploads from ground stations, because even small drifts can degrade positional accuracy to several meters. Imagine standing at sea level while someone stands atop a mountain. Their clock ticks faster by tiny fractions. Over decades, the difference accumulates. A lesser-known medical and psychological note: humans have difficulty intuitively grasping exponential and relativistic scales, leading to persistent misconceptions about time travel possibilities. Something goes wrong in your imagined spacecraft. Not an explosion, a miscalculation. Fuel margins underestimated by 2%. A lesser-known technical constraint of rocket design is the tyranny of the rocket equation, where required propellant mass grows exponentially with desired velocity. Change. Now the cost becomes clear. To truly leap centuries into the future through velocity alone would require speeds so close to light that energy requirements exceed current global production capacity. A lesser-known countermeasure concept in theoretical physics is the Alcubierre warp drive, which mathematically allows faster-than-light effective travel but requires exotic negative energy densities not known to exist in usable quantities. Your heart rate slows as realization sets in. Time travel forward is real, but tiny. Time travel backward remains unsupported by experimental evidence. A lesser-known procurement politics factor in fundamental physics is that large-scale collider. Funding often competes with climate and medical research budgets, shaping pace of discovery. You sit in the quiet lab again, 2 clocks, one slightly ahead, that is the future. A lesser-known technical fact: gravitational time dilation near a black hole becomes extreme, with time near the event horizon slowing dramatically relative to distant observers. But approaching the black hole is not cinematic heroism. It is lethal radiation and tidal forces. A lesser-known medical detail: spaghettification near a stellar mass black hole would stretch a human body due to tidal gravity differences long before crossing the event horizon. The real reason time travel is not what you think is scale. Effects exist, measurable and operational, but they are subtle and bound by energy and gravity. A lesser-known battlefield adaptation of relativity is embedded in every smartphone GPS chip, which performs relativistic corrections invisibly billions of times per day. In the end, both tracks meet here. Time travel is not a door. It is a correction factor. It is engineering discipline layered over abstract mathematics, and the true shock is quiet. You are already moving through time at 1 second per second, and the universe allows only modest deviations unless you are willing to pay with energy measured in stars.